Good morning, on and all present here. I'm Nandini, working as an assistant professor in SNS College of Technology, the Department of Computer Science and Technology. Today, we are going to see a topic on what is normalization flow in the subject generative AI. So, first of all, we are empathizing this normalization flow. In machine learning, we often deal with many complex data distributions, which are known as images, audios, text, files, document, etc. These are all a complex distribution. So these are hard to model directly. So we need a method to understand the data probability, generate a new data, maintain the exact likelihood functions. So these are all who faces this needs, what they think feel. These are the distributions that we are seeing. So AI researchers and ML engineers need data scientists handling high dimensional data, deep learning practitioners, generative model developers. So why we need is two pain points, what they extract, how they are stable, how it is efficiently and scalable. So this problem statement here is, so this normalization flow model aims mainly at how it is likelihood exactly, how the model is trained, how this efficient sample generates, how this particular for high dimensional data by transferring into complex through a sequence of invertible things. So how we are understanding this or how we are defining this problem. The challenge is how we can transform a simple distribution into a complex real world distribution while keeping a calculated traceable. For example, in traditional generative models, either approximate probability or an difficult to train. There are two models. So we should model it in the form of how it is extracted, how it is invertible, how it is efficient. So, exact likelihood estimation is trying to build a model for likelihood estimation. It is trained in high dimensional data. So, it is easily estimated, stably trained, and effectively scalable for sampling. So, how it has been ideated. So, this normalization flow is based on the idea of transferring start with a simple distribution like Gaussian distribution, which applies a sequence of invertible transformation, which gets a complex distribution. This is based on the change of variable formulas. So we have some core components like base distribution, flow transformation, and exact probability computation. This base distribution is also known as a simple distribution. This flow transformation is also known as an invertible functions. So this has no loss of information and enable reversible transformations have been done in this ideate phase. So this ideate phase shows an normalization flow method with the help of this diagram with the generative model images, how it does density based clustering, time series, probabilistic time series, likelihood, high dimension, etc. So next, how a prototype has been defined here. This prototype has a step-by-step process. First one is sample from a simple distribution. Example, Gaussian. Apply multiple invertible transformations. So again and again, you should transform it. Transform into complex data. Important property. Each transformation must be invertible, which allows data to latent encoding, latent to data, which is generated. If data has been latent, it is encoding. If a latent has been changed as data, it is generated. This probability is computed using Jacobian determination. This ensures how exact the likelihood function and how efficient this training is. So this normalization flow, how it is built of normalization flow with latent space, data spaces. Latent space is invertible to data spaces. This diagram correctly explains a forward F1, F2 with an inverse diagram. So it is a chain of invertible transformation which is used for complex data distributions. So this building a normalization flow product PZ to PX is known as F2. So chain invertible transformation, forward and invisible transformation is being shown here. So normalization flow, key concepts are given here. There are some change of variable formulas, log likelihood expressions, multi-step flow transformation. So the last part is a testing part. In this testing part, this normalization flow are used in image generation, density estimation, anomaly reduction, variational inferences. So these results will be in high quality data generation, extract probability calculations, better invertible comparable list. So these are all an evaluation matrices. So a mind map is shown here. Thank you so much for the video.